Dear friends, I am very excited to introduce you to neural networks and deep learning, the discipline through which computers replicate the pattern recognition abilities of the human brain. Since neural networks are the gateway to extensive levels of creativity, including both image and text recognition, I believe their virtues are best captured by literature on neuroscience and the practical tactics of self-concept and identity shifting. These are the stages we can expect in our new journey. 1. Prepare data, curate experiences. 2. Build model, structure the mind. 3. Define loss plus optimizer, set feedback loops and habits. 4. Train, deliberate practice. 5. Validate, reflection and self-assessment. 6. Save model, internalize learnings. 7. Load model for inference, recall and apply wisdom. 8. Deploy/integrate, manifest potential in reality. We start with our data. Just as a model requires high-quality input, our self-image feeds on experience. Use data sets of empowering memories, habits, and affirmations. We can either use an existing dataset or create a custom one. If we choose an existing dataset, we focus on the following parameters. Root signals the directory containing the data. Train, true, false, specifies whether we use the data for training or testing. These are the experiences we actively practice. Download indicates whether we use data stored online if not available at root. Transform and target. Transform indicate the feature and label transformations. The target reflects the self-image we want to achieve. After creating a dataset, PyTorch requires a data loader to batch, shuffle, and handle parallel loading. In real-world training, especially for images, we nearly always use transforms. Compose, for chaining multiple transformations in sequence. Normalization to scale input data or layer activations to a standard range. For us, normalization means scaling experiences so no memory dominates disproportionately, balancing our mental input. Data augmentation, training only, improves robustness by generating additional samples. In our mind, augmentation means creatively reinterpreting experiences to build resilience, just as we expand image datasets with rotations and flips. Batching and shuffling teaches us flexibility and attention. We begin our neural network project by setting up our device, the virtual area where computations happen. It's vital that PyTorch knows where to store and run our models, as errors occur if we mix tensors across devices. The device is your mental workspace, so our next challenge is choosing our cognitive environment. Moving your model, mind, and inputs, experiences, to the right environment enables optimal learning. We can choose between CPU, Central Processing Unit, default. For us, everyday awareness. GPU, Graphics Processing Unit, much faster. For us, a high-focus, enriched environment. Just as we create a dataset class, define the boundaries of your reality. If we opt for creating a custom dataset, we focus on 3 functions. Init, initializing the directory, which includes the data and annotations. This is identifying our experiences. Len, to obtain the number of samples in our dataset or measure how many lessons you've internalized. Gettytim, uses a given index to return a sample from the dataset, like retrieving empowering memories to guide our actions. We then split the dataset into the input X and output Y. Our deep learning model will have to switch between 2 modes, training and evaluation. X, input, current thoughts, habits, sensory experiences. Y, target, aspirational self-image and goals. Our brain must switch between training mode, learning, and evaluation mode, reflecting. We've reached the stage in which we define the model. We create a class from the NN.model. Some of the most frequent models we can choose from include 1. Sequential models, basic NN, recommended for simple problems such as linear regression or basic classification. They are structured in layers which have received an input and pass an input. For us, it's our simple habits and routines. 2. Convolutional neural networks, CNNs, use local filters, kernels, to detect patterns, best to be applied on spatial data such as images and video. That's our pattern recognition. See opportunities and threats in your environment. 3. Transformers use sequence modeling with self-attention, shining in NLPS, image generation, and time series forecasting. For us, that would be process complex sequences, like emotions or goals over time. 4. Autoencoders are used for compression and reconstruction, such as recognizing images, anomaly detection, and dimensionality reduction. Just like us when we compress old memories and reconstruct useful lessons. 5. Generative adversarial networks, GANs, are behind art generation, style transfer, and even realistic images such as deepfakes. That's like our mind when we generate creativity and novel ideas. 6. Graph neural networks, GNNS, operate with structured data, nodes, and edges to create social network analysis, recommendation systems, and molecule modeling. Think of our relationships and social networks. We initialize the model as a class object with number of inputs as attribute. The inputs are distributed by layers defined by weight and nonlinearity. The parameters in a model describe its trainable parts. An init function defines the layers and activation functions of the network. An activation function introduces nonlinearity into the model, which is essential for the network to learn complex patterns beyond simple linear relationships. So what activation functions can we choose from? Sigmoid for probabilistic outputs and binary classification. Just like us when we evaluate probabilities and take binary decisions. TNH, hyperbolic tangent, in which outputs are zero-centered, which helps convergence. Best for RNNs. In our mind, that implies centering our emotional response. ReLU, rectified linear unit, which introduces sparsity and activates only some neurons. Recommended for CNNs and deep models. In our mind, that would be like energizing positive neurons. Leaky ReLU fixes dead neuron problem of ReLU by allowing a small gradient when x less than 0. Offers robustness to deeper CNNs. This implies maintaining resilience even in low states GALU, Gaussian error linear unit, used in transformers and NLP for its MUTH, differentiable probabilistic gating mechanism. For us, that's the smooth integration of complex inputs such as significant life events. Linear, identity function, provides no actual transformation upon the input, but it activates the output layers in regression. The model class carries a forward propagation, which allows specifying how data will pass through the network, propagates the input to the first layer and so on, and releases the output through the last one. For us, that means translating inputs into real-life action. After you initialize the model, you calculate the loss function, or how wrong we are. In real life, loss measures the gap between current self and desired self. We can opt for the following loss function, nn.mse loss, mean square error. For regression tasks, nn.nll loss, negative log likelihood. For classification, nn.cross entropy loss, a combination between nn.log softmax and nn.nll loss. We got out loss function, so now we optimize the model or improve its performance. The model.parameters tells the optimizer what weights to adjust. The state.dict function allows us to access all parameters within a model, whether trainable or not. The learning rate indicates how big the steps should be when learning. The epoch, which implies a rotation around the data, is divided in mini badges of inputs and targets in the training data. In this stage, we define the optimization by indicating the criterion and the optimizer applied on the model parameters, learning rate, and momentum. It's exactly like us when we're adjusting our behavior. Optimization implies a three-stage process. After each iteration, we call optimizer.0_grad to clear old mistakes and reset the gradients of model parameters. We use the loss.backward to backpropagate the prediction loss. The backward propagation pass calculates the loss and adjusts parameters. Don't worry, the heavy math is conducted under the hood by autograph, so yes, humans don't have to do calculus by hand. We call the optimizer dot step to apply the fixes by adjusting the parameters highlighted in backward propagation. We can use some of the following optimizers: SGD, stochastic gradient, Dissent can be applied on simple tasks, textbook problems, which demand fine-tuning with low noise, such as exploratory learning. SGD plus momentum delivers better convergence without full-on adaptivity, perfect when we are focused on observing stability and ignore volatile short-term gradients. ADAM, adaptive moment estimation, is perhaps the most popular optimizer, as it handles both heterogeneous input as well as sparse data or non-stationary problems. ADAM also provides the benefit of keeping track of the average of past gradients, momentum. RMS prop highlights a similar performance to ADAM, but without the momentum of the gradient, best shining on time series or online learning, also handling non-stationary patterns such as financial markets. AdaGrad/Ada Delta performs on very sparse data. After calculating the loss and optimization, we can report the training progress by using TQDM. For each epoch and the number of epochs, we separate the data in batches per epoch and calculate the loss and accuracy through the forward function. If we're unsatisfied with the results, we use the backward function to optimizer.zeroGrade and loss.backward, and to further update the weights through optimizer.step. We then evaluate the model at the end of the epoch. When dealing with limited data, high model complexity, or when the network is prone to memorizing noise, we should also include regularization techniques. Dropout layers prevent overfitting by randomly deactivating a fraction of neurons during training. In real life, it reflects releasing unhelpful patterns. Early stopping prevent overfitting by monitoring the model on a separate validation dataset during training and automatically halting the process when performance stops improving. For us, it's pausing before burnout. Weight decay restructuring models from overfitting when underparameterized, or guide them towards simpler interpolations if overparameterized. In real life, it's simplifying our metal model. Training loop. The model.train method enables layers to learn and update parameters through a series of operations, which adjusts parameters to minimize the error in predictions. For us, it's like focused practice. The typical training iteration for a single batch follows these steps. 1. Model.train. This function sets the model to training mode. Within the model.train method, the dropout and batch norm behave differently from their work in evaluation. In training mode, dropout layers randomly drop some connections to prevent overfitting. Batch norm layers use per batch statistics to normalize the data. It is vital to introduce the optimizer.zeroGrad method within the training, which allows us to clear any gradients which accumulate during each iteration, affecting parameter updates. Through the optimizer.zero_grad, we get a fresh calculation as the gradients of all model parameters are refreshed to 0. As previously mentioned, the forward pass guides the data flow, making predictions on the output. For us, it would be trying new behaviors. The loss calculation is based on the difference between the actual target labels and the predictions. The backward pass then calculates the gradient of the loss, or how much parameters need to be adjusted to reduce it. It's exactly like us when we reflect and adjust. The optimizer uses the calculated gradients to update the model's weights and biases according to the chosen optimization algorithm. This is the actual learning step where the model parameters are refined. Applied to human psychology, the optimizer.step implies integrating lessons into life. In order to monitor the progress we reached from one iteration to another, we can use the TQDM library, which display various metrics, including iterations per second, percentage completed, and estimated time remaining. The model.eval freezes the model's parameters and ensures deterministic, non-learning behavior. The torch.nograd method prevents PyTorch from tracking gradients during evaluation. Without this, inference is slower and uses more memory. While model.eval is like a moment of pause and reflection with no active learning, torch.nograd is like a state of observation without judgment. We are now ready to evaluate the model on distinctive metrics. For classification, we use accuracy, which measures the overall percentage of correct predictions; precision, which measures the proportion of positive identifications that were actually correct and is important when false positives are costly; recall, or sensitivity, measures the ability of the model to find all the relevant cases and is crucial when false negatives are costly. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances both, especially useful for imbalanced datasets. Precision and recall are like us when we measure alignment with true goals, while F1 score allows us to balance effort and outcome. For regression, root mean squared error, RMSE, gives more weight to large errors, while mean absolute error, MAE, provides a linear average of error magnitudes. For computer vision, IOU calculates the overlap area between the predicted bounding box, segmentation, and the ground truth. For natural language processing, BLEU evaluates the quality of text which has been machine translated from one natural language to another. We now save our model with the load state dictee method, used to load a model's learned parameters, weights, and biases from a saved state dictionary. For us, saving feels like empowering mental patterns and recalling them during challenges. We now make predictions on new data. For us, this is applying learned patterns to new situations, action as the final proof of learning. So, my friends, if we were to apply the processes behind neural networks to our own lives, your self-image is a model. Train it deliberately, evaluate often, and feed it empowering inputs. Failure is a deviation, not an identity. Update your parameters and continue. Habits are weight updates. Small, repeated adjustments shape long-term identity. Environment is your device. It amplifies or constrains learning. Reflection equals evaluation. Action equals inference. Mastery equals deployment in real life.